Hello everyone, today we will present our final project for the differential equations course. Our project is about modeling and simulating a 3D pendulum using Python and numerical methods. Let's start with a simple idea. We are all familiar with a regular pendulum. For example, a clock pendulum or a weight hanging on a string. In all these cases, the motion is limited to one plane. It just swings back and forth. But in real life, motion is often more complex. For example, if you slightly push pendulum sideways, it doesn't stay in one plane anymore. A hanging cable or object can start moving in circles or spirals, as an example in presentation swinging chandelier. These are examples of three-dimensional motion. In our project, we study exactly this case, a pendulum that is free to move in all directions in space. Because of this freedom, the motion becomes more complex, the system becomes non-linear, and simple formulas are no longer enough. That's why we use differential equation and numerical methods to understand and stimulate its behavior. Choosing the right coordinates. Now an important question is, how do we describe the position of the pendulum? At first glance, we could use Cartesian coordinates x, y, and z. But there is a problem. The pendulum is attached to a rigid rod to constant length, so its position must always satisfy a constraint. The distance from the pivot point is fixed. Because of this, using x, y, z becomes complicated. We would always need to enforce this constraint. Instead, we use angular coordinates, which naturally include this condition. We define two angles: theta, the angle between the rod and the vertical direction, and phi, the rotation around the vertical axis. With these two variables, the position of pendulum is fully determined, so instead of tracking position directly, we track how these angles change over time.
During the equation, now let's talk about where the equation come from, or we start from a fundamental principle of physics, Newton's second law. The pendulums are affected by two forces: gravity acting downward and tension acting along the rod. His key idea: the tension force does not influence the angular motion directly. It only uses that the length of the pendulum remains constant, so the motion we'll observe is mainly due to gravity. To get the equation, we express the point is term of theta and p. Compute velocity and oscillation project force and angle decreations apply Newton law. After doing this, we ambition a system of the differential equations. One describes how theta evolves, the other describes how phi evolves. The equation contains trigonometric functions and products of variable nonlinear terms. This makes the system nonlinear and complete. And because of that, we can't solve it using simple formulas. Why numerical methods? Since we can't find the exact solution, we use numerical methods. The idea of numerical solving is simple. Instead of solving the equation directly, we simulate the motion step by step in time. We start from initial condition. One, it's initial angles. Two, it's initial velocities. Then we compute how the system evolves over very small time intervals. For this, we use the Runge-Kutta method, RK45. This method is powerful because it gives good accuracy. It automatically adjusts the step size. It keeps numerical error under control. So instead of choosing a fixed step, the algorithm adapts during computation.
From equations to codes, now let's connect the mathematics to our implementation. We used Python with three main libraries: NumPy for numerical computations, SciPy for solving differential equations, matplotlib for visualization. In SciPy we use the function solve IVP. This function takes the system of equations, initial conditions, and time interval, and returns the solution over time, but the result is still in terms of theta and phi. So to visualize the motion, we convert them into Cartesian coordinates. X equal to L multiplied to sinus theta multiplied to cosinus of phi. Y it's L multiplied to sinus theta multiplied to sinus phi. Z equal minus L multiplied to cosinus theta. This step is important because it transforms abstract variables into physical position. Finally, we animate the pendulum motion in 3D space. Results and interpretation. Now let's look at the results. The animation shows the trajectory of the pendulum. One important observation is the motion strongly depends on initial conditions. For example, small initial angles, it's smooth, almost periodic motion. Larger angles, it's more complex trajectories. Certain conditions, irregular or chaotic-like behavior. This shows that the system is highly sensitive. Even small changes at beginning can lead to very different outcomes. This is a key feature of non-linear systems.
Okay, so now let's take a deeper look at error analysis. An important point to understand is that in nonlinear systems like the 3D pendulum, errors do not simply stay small. They can grow and significantly affect the solution over time. Error propagation. First, numerical errors act like small perturbations in the system. What this means? And it means that even tiny inaccuracies introduced at each step can evolve and amplify. Because the system is non-linear, this growth is not necessarily linear. In some cases, it can become very large over time. Local, we see global error. So we have like two types of error analysis. The RK45 method we used controls local truncation error, meaning the error at each individual step is kept small. However, it is important to note that controlling local error does not guarantee global accuracy. As the simulation progresses, these small errors accumulate and the overall trajectory may deviate from the true solution. Sensitivity to initial conditions. Another key aspect is sensitivity to initial conditions. From a mathematical point of view, the system behaves in a way where small changes in the initial state lead to a very different outcomes. Numerical error effectively acts like a small change in initial conditions. As a result, even a highly accurate method can produce trajectories that diverge over time. And energy drift. So let's consider about physical consistency. In theory, the total mechanical energy of the pendulum should remain constant. However, in our simulation, we may observe energy drift. This happens because RK45 is not an energy-preserving or symplectic method. So over time, energy may slowly increase or decrease, and the motion becomes slightly unrealistic. Numerical stability. There are also stability issues related to the equations themselves. For example, when the angle becomes very small, terms like sin approach zero, which can reduce numerical precision. This can introduce instability or inaccuracies in the computation. To summarize, error analysis in this system is not just about making the step size smaller. It's about understanding how errors propagate, how they affect long-term behavior, and how well the numerical method preserves physical properties. The key takeaway is that in nonlinear system, even small numerical errors can fundamentally change the outcome. And in conclusion, in this project, we modeled a 3D pendulum using differential equations derived from physical laws. Because the system is nonlinear and complex, we used the numerical method Wunsch-Kutta to approximate the solution. We then visualized the motion and observed how sensitive and dynamic the system is. This project demonstrates how mathematics, physics, and programming work together to solve real-world problems. Thank you for your attention. That's it.